Seoul National University. He will give a talk on stability of um multiple lamp dipoles. Let's welcome.
Okay, thank you very much, Professor Rizalji, for the kind introduction. And thanks a lot, Hong, for invitation. It's really great opportunity to be able to speak here in a large audience. And this is a work on stability of lambda dipoles, and it's joined with Ken Abe from Osaka, Kyudong Choi from UNIST in Korea, and Yao Yao from Singapore. And please don't hesitate to interrupt me if you have any questions. Um, so can you guys see the slide moving? Just checking.
Yes,
Yep.
yes. Go ahead.
Okay, great. Great. So I'm very interested in the long-time dynamics of 2D incompressible fluids, and Dio gave a very nice talk on this topic a few days ago. And the key observation, which comes from both numerical and experimental studies, is that after a long time, the vorticity concentrates or condenses near just a few points in space. And they remain like that for infinitely long times. For instance, relatively recent numerical computations of Modin and Viviani shows that numerically on the sphere, starting from random vorticity, you eventually get to either 2, 3, or 4 vortices. So here is a picture when you have 4 vortices as time goes to infinity. And this condensation phenomena, the proof is basically completely open. However, for this condensation to be correct, we need to be at least prove that once the vorticity is sufficiently concentrated near a few points, such configurations remain stable for the rest of the time. And unfortunately, even this much simpler question is widely open when there are more than 2 vortices in the domain. So this is the motivation. So let me just introduce the vorticity equation into the incompressible flow. So I consider vorticity as the main variable. It's just transported by the velocity u, which is determined by the vorticity by this Biot-Savart law. You invert Laplacian and take gradient pulp, which is just a curve. And throughout the talk, I will assume for simplicity that the vorticity at each moment of time is odd symmetric in the x2 variable. So if you flip sign in x2, the vorticity flips sign. And furthermore, it has sign condition, which is that vorticity is non-negative on the upper half plane. So I will assume these two conditions. They are motivated from the study of vortex rings, and these conditions are preserved in time. So originally, the study of traveling waves in 2D had largely motivated from the study of vortex rings, where 2D vorticity equation can be viewed as a simplified model of the dynamics of cross-section of vortex rings under axis symmetry. Okay. So we will see later this picture is the lambda dipole. It's a nice example satisfying these two conditions. So if we assume this odd symmetry, we can just consider the vorticity on the upper half plane. It's a reduction of domain. Okay. So I will just consider vorticity as defined on the upper half plane. And if you assume this sign condition, the nice thing is that you get a new monotone quantity. So what's the new monotone quantity, if you take the time derivative of x1 times omega, then this is a general formula. The time derivative equals u1 omega integrated in space. And if you expand u1 in terms of the integral against omega, the Biot-Savart law in the half plane, this is the exact formula you get. So the sign condition is preserved in time. So this product of vorticities is non-negative. And you see that this kernel is non-negative on the upper half plane, where x2 and y2 are both positive. So this quantity is non-negative. So what does it mean? It means that space integral of x1 omega is increasing in time. In average, particles are moving to the right. And a non-trivial statement proved by Iftimi is that this time derivative globally in time has a lower bound depending only on the initial data. So while it is trivial that this time derivative is non-negative, it's non-trivial that it has a global in time lower bound. It also has a global in time upper bound. So this means that this quantity, the x1 average on the vorticity support, is linearly growing with time. So everything is moving to the right in average. Then along these lines, one can formulate a conjecture, which is that if you assume the sign condition on the initial vorticity, you can imagine that after a long time, some faster part will separate itself from the rest of the vorticity. And once they are separated, you can think of applying this inequality to each of the separate pieces and show, hopefully, that they further and further separate. So one can raise a general conjecture that general initial data under at least the sign condition split into a few traveling wave-like objects and separates in spaces. Time goes to infinity. And in this talk, I want to describe you some definite results in this direction. But the conjecture is wide open. So a quick outline, I want to first review the variational principle, basically energy maximization under constraints. This gives stability of vortex, which is concentrated near a single point, basically. So that's the disadvantage of the variational principle. It gives stability only for the global energy maximizer. So lambda-dipole, as a special case of this variational principle, we can get stability of a single lambda-dipole. And our main result is the stability of multiple lambda-dipoles, meaning that we consider linear superpositions of lambda-dipoles. And of course, in this case, the challenge is coming from interactions of these dipoles. And the key point is to combine variational principle with a Lagrangian bootstrapping scheme, which basically means that we use the transport nature of the vorticity equation. We follow trajectories of particles and see how they interact through the flow map. And I will finish with potential extensions and remaining problems. So we start from really the basics. A traveling wave is a solution which has some profile omega bar, and the time dynamics is just shift in space. And we will always assume that the shift is towards the positive x1 direction, and w is the traveling speed. I will show you some pictures and it will become clear what it really means. And there is this program originally formulated by Kelvin for vortex rings and written down rigorously by Benjamin. This is to do the following. You construct traveling waves and at the same time obtain their stability by solving an energy maximization problem under natural constraints. So if you do not put any constraints, then energy maximum doesn't make sense. You want to put constraints which are natural in terms of the Euler equations. And within that constraints, you want to find the energy maximizer. Then the non-trivial statement is that maximizer exists and it's a traveling wave and it's dynamically stable. So if you are just interested in proving existence of traveling waves, there are a lot of approaches. And one of the very successful one is using bifurcation theory or some reduction methods using semi-linear elliptic, but usually you cannot get dynamical stability that way. Okay. So I will give you a very concrete example of Benjamin's variational problem in the 2D case. So on the upper half plane, we consider the following admissible class. So this is just a simple example of an admissible class. So recall vorticity, we consider it to be non-negative on the upper half plane. And the L1 norm is circulation of the fluid is bounded by some parameter m. And let's say the L2 norm is bounded by 1, normalized. And this weighted L1 norm, which I write as L1 star, this is just x2 times omega in L1. Let's say it's also bounded by 1. So this is an admissible class parameterized by the mass m. So they correspond to circulation entropy and impulse. So in the physics literature, this integral is called the impulse of the fluid. Then the variational problem asks you to find who is the kinetic energy maximizer in this class AM. So what is the kinetic energy? I view kinetic energy as a functional of the vorticity, and it's computed explicitly as the half of L2 norm squared of the corresponding velocity. So if you have omega, this expression is the corresponding velocity, and then you take the L2 norm squared and divide by half. And in the case of the upper half plane, the energy has a very nice explicit kernel in terms of the vorticity. So it's a double integral because energy is a quadratic quantity, and the kernel is exactly this log function. And this shape of the energy kernel shows why it is not so easy to find compactness of maximizing sequences. So what you do is you have this admissible class on which you want to maximize this energy. And what you can do always is to extract what is called maximizing sequence of vorticities in the admissible class, along which the energy takes the supremum value. In principle, it could be infinite, but we want to rule it out. And here is basically the idea, why and how it works. So what we want is strong compactness of maximizing sequences in this admissible class. So this admissible class, recall that it has 3 bounds, L1, L2, and impulse weighted L1. So L1 bound essentially controls the support size of maximizing sequences. And L2 bound controls Dirac delta concentration. So if you look at this formula, it has a singularity when X and Y becomes too close. So if omega concentrates like Dirac delta, energy becomes infinite. But of course, that is impossible if you assume any quantity which is strictly stronger than L1. So for L2 to be bounded by 1, it cannot concentrate like Dirac. And that rules out the difficulty coming from this singularity in the kernel. And for traveling waves, the key point is to use this impulse, and this controls the distance from the boundary. And let's see why this is necessary. If you just consider L1 and L2, these two norms are translation invariant. If you translate the vorticity in the upper half plane, L1 and L2 remains the same. But then what you can do is you can slide the vorticity towards the infinite x2 direction. You just slide the vorticity upwards in space. Then L1 and L2 norm remain the same. But this kernel log blows up as x2 and y2 goes to infinite. So energy does not have an upper bound if you just assume these two bounds. And L1 star is the weighted L1 norm with weight x2. So basically, it controls how far the maximizing sequence can be in average from the boundary. So that's the theorem, which is done by a sequence of papers culminating in quite recent works of Abe Choi and Kao-Chin Zhao Zhou. So the conclusion is that if you consider this admissible class AM, for any M, maximizers exist and they are stable traveling waves. Okay? And in asymptotic regimes, you can get better description. So in the asymptotic regime, when M is very small, so very small mass case, maximizer is unique, and it's asymptotically circular, which is very far from the boundary. Okay. And what we will focus is the other extreme limit when M is very large. So in principle, as M becomes larger, the maximizer becomes larger and larger in terms of support size. And in principle, the support size can diverge to infinity. But this work of Abe and Choi proved that it's actually not the case. There is a threshold of mass where the maximizer becomes completely independent of the mass constraint, and it's unique, and it's actually given by what is called the lambda dipole. And here is kind of bifurcation diagram. So starting from very small mass, you have a dipole far away from the boundary of the half plane. As you increase the mass constraint, they come down with their supports becoming larger and larger. And then there is a critical point when you get this lambda dipole, and then maximizer just stays as the lambda dipole, even if you further increase the mass constraint. So I hope this picture is kind of clear. So just some more information about the lambda dipole. What's very interesting is that it has an explicit form given by Bessel functions. It's not so surprising if you recall that the Bessel functions is an eigenfunction for the Laplacian. So in the applied literature, people usually parameterize the family of lambda dipoles using the speed parameter W. This is really the traveling speed of the lambda dipole, and the support radius R. So lambda dipole, as this formula shows, has vorticity supported in a bore of radius R. Okay, so this function is harmonic, so its Laplacian is exactly 0. Okay? So the vorticity, the lambda dipole, has support of bore, and it's a two-parameter family of traveling waves, parameterized by speed and radius. But for our purposes, turns out to be very natural to parameterize them using the L2 norm and the impulse weighted L1 norm. So for any kappa and mu, so previously I normalized them to be 1 and 1. That gives a normalized lambda dipole. But if you now generalize it to be kappa and mu for positive constants, and then in this new admissible class, the unique energy maximizer is the lambda dipole whose L2 norm is kappa and whose impulse is mu. And the speed of the lambda dipole is directly proportional to kappa. And it's not surprising because L2 norm of the vorticity in 2D scales like L infinity of the velocity. Okay? And there is x1 shift. So if you shift a lambda dipole, it does not change the energy. So when I say lambda dipole is the unique energy maximizer, uniqueness is up to these shifts in the x1 direction, which is the traveling direction. Okay, so the main result of Abe and Choi was that, so this is actually reformulated version, but the main theorem is the following. In this admissible class, A kappa mu, if the vorticity omega belongs to this admissible class, and if the energy of the vorticity is almost energy of the maximizer, which is the lambda dipole, then omega must be close to some shift of the lambda dipole. So this is what I call kinematic theorem, because there is no dynamics. It's a purely functional analytic statement. Okay? This kappa and mu, and for any epsilon there is delta, such that if omega has too much energy, then it must be close to a translate of the lambda dipole. Okay? So stability, dynamical stability of a lambda dipole is a corollary of this kinematic theorem, simply because all the quantities involved in this kinematic statement are invariants of the dynamical system. So just to make sure, I write down the precise stability statement for a lambda dipole. If you start with an initial data, omega 0 of 2D Euler, okay, which is close enough to the lambda dipole at the initial time, then the global in time solution to 2D Euler with this initial data stays close for a time to some shift of the lambda. Okay? So this is a stability statement, and this is really a corollary of the kinematic statement, simply because all the constraints we use together with the energy are invariants in time. And here I want to emphasize one thing which will be important from now on, which is that although the lambda dipole is a traveling wave, in the moving frame, its velocity field is highly non-trivial, and in particular, so this is the streamlines in the moving frame, the frame moving together with the lambda dipole. So the lambda dipole itself is of course steady in the moving frame, but the velocity field generated by a lambda dipole basically transports everything towards its rear. It flushes really everything outside towards its rear. And this feature of the lambda dipole will be very important from now on. So that feature is directly responsible for a phenomena called filamentation, and it's very intuitive. So if you put a general perturbation outside the lambda dipole, remember that the velocity of the lambda dipole flushes away perturbations towards its rear. And then the perturbation will become longer and longer in time because the speed of the perturbation is strictly slower than the speed of the lambda dipole. So you expect that the diameter of this perturbation becomes longer and longer linearly in time, and that's what we can actually prove. So we can prove that diameter of the support in general grows linearly in time. And the main ingredient on this proof is to actually obtain a quantitative estimate on the shift function, tau t. So this tau t was coming from this stability statement. So if you just apply the kinematic statement, it does not have any dynamical information. So this tau t is some abstract thing which we exist, but without any information. But actually by tracking the dynamics, you can prove that tau t is essentially W times t, which is of course expected. This is the amount of shift for the lambda dipole, and tau t is the shift of the perturbation. So this shows appearance of filamentation, but the numerics is not very good. Anyways, so the question we ask is, can we prove stability of superpositions of lambda dipoles? And there are serious issues. First is this filamentation. So if you just consider two lambda dipoles, no matter how far they are initially, they will eventually become connected by the filaments they generate. So we cannot use separation of support. And if you have a vortex, basically energy maximization principle is the only known way to prove stability. However, energy really favors concentrated states. So what you can prove easily is that once you superposition several traveling waves, okay, no matter how far they are from each other, such a configuration is never an energy maximizer, even locally in the phase space of vorticities. No matter what constraints you put, the constraint should be preserved by the Euler equation. Okay. So this is the key difficulty. The only way so far to prove stability of dipoles is to use the energy maximization principle. But once you have just two dipoles, it's never an energy maximizer, even locally, simply because energy has some convexity which favors concentration. Okay? If the vorticity concentrates, it has higher energy. And conservation laws in Euler cannot really distinguish perturbations which are far away. So our approach, the idea is very simple, is to combine variational principle together with Lagrangian bootstrapping scheme, which is to really track the vorticity particles, how they move in space, and then calculate the total amount of interactions between various parts of the solution. So here is our main theorem, which is the stability of multiple lambda dipoles. So in words, it just says that finite linear combinations of the lambda dipoles are stable if they are ordered in space and initially far apart. So there are two conditions which are absolutely necessary. First of all, they need to be ordered in speeds. It means that the fastest one initially is in the far right, second fastest, the second right, and so on, and the slowest guy in the far left. Okay? So if the slower one is in front of a faster one, then faster one will catch up and they will collide. And we don't know what happens after collision. And furthermore, they need to be initially far apart. So this is the condition that they're initially far apart. Okay. So let me read the theorem. So for any epsilon, there is some small delta and a distance such that if the initial vorticity is sufficiently close to this linear superposition of n lambda dipoles, and lambda dipole has parameters kappa I and mu I, and kappa I to kappa I, so they are ordered. Okay? And then the conclusion is that the solution satisfies the same property. The solution for all positive times remains close to the same linear combinations of the lambda dipoles, but we need to shift each lambda dipole with respect to its own speed. So dit moves with speed of the ith lambda dipole. Okay, so this is the theorem. And any questions about the statement? Okay, so I just want to emphasize that the statement is non-trivial even when the initial data is exactly the linear superposition of lambda dipoles. It's because even in that case, they start interacting immediately, and then there are mechanisms which can boost up the following lambda dipole. Okay? And I want to also point out one thing. Lambda dipoles are parameterized by kappa and mu, and it is only kappa which determines the speed. And in our theorem, we do not need any condition on relations between mu for each of these lambda dipoles. And the consequence is that potentially a larger lambda dipole can be in the back, and it doesn't matter. The size of the lambda dipoles do not matter. It only matters that the fastest one is at the right, second fastest next, and so on. So some comments on the literature. So in the dispersive community, Martin, Mayer, and Tsai has a pioneering work for GKDV solitons. So their main theorem is almost identical to our statement, but they also have asymptotic result. So GKDV solitons, they are just parameterized by the speed. So it's a one parameter family of solitons. And in our case, the lambda dipoles comes in 2-parameter family, and that is one of the main extra challenges in our case. Of course, the equations are completely different. And for Euler, there is a pioneering work of Iftimi, Lopez, and Lopez. So they proved a very similar result when you consider point vortices on the upper half plane. And here's the key observation. If 2 point vortices on the upper half plane are distance d apart, the interaction velocity they generate on each other decays like 1/d squared. And this effect, 1/d squared, is integrable in time if the vortices separate at least linearly in space. Okay? So in the case of point vortices, you can use in space support separation together with this decay estimate, which immediately gives the stability result for multiple point vortices. And except for this point vortex case, our result seems to be the first multi-soliton stability for 2D incompressible Euler. And there can be many generalizations where you replace lambda dipole by other stable dipoles. It's not that much more difficult. So just to make sure that we are on the same page, I want to show you dynamics of the point vortices. So when I say point vortices on the upper half plane, you can imagine a pair of point vortices in the full plane, one positive and one negative, and it defines a traveling wave. Okay? So the first picture shows that when the faster one is in front, they just separate and remain stable. It's very expected, right? But what I want to show you now is that even if the faster one is in front, if the distance is kind of close, then it's not stable. Okay? So initially the faster one was in the front, but the distance was close so that they actually switch their orders. So this is called leapfrogging. Okay? So you see that there is an effect which accelerates the particles in the back. And this becomes the main enemy in our proof. And this mechanism appears clearly already in the point vortex case. So in the remaining time, I just want to sketch the proof in the case of 2 lambda dipoles. Okay? So assuming that everything goes well as planned, we have expected shift estimate. Omega I expected near this point. Okay? And we use hard cutoff of the solution using the midpoint of 2 expected locations. Okay? So omega is the solution with our initial data. You cut it after some borderline and define it to be omega 1. And you just define the remaining part to be omega 2. And the goal is to apply the kinematic statement for each of these pieces. Then what do we need for the kinematic statement to apply? We need upper bounds on L2 norms and the impulse for each of them, and lower bounds for the individual energies. So what we do is we write these conditions as our bootstrap assumptions. The point is that once we have all these bootstrap hypotheses up to some time t, then from 0 to time t, we have our stability statement. So the key challenges are filamentation, the lift-off effect, I will explain this now, and existence of energy unfavorable regime, and finally, unknown relation between epsilon and delta. So here, delta is the initial closeness parameter, and epsilon is the closest parameter from the stability state. And you notice that the bootstrap hypothesis, which we need to propagate globally in time, are written in terms of delta and not epsilons. So what does it mean? It means that the conclusion that we prove, it only gives epsilon closeness. The conclusion itself is useless in closing the bootstrap hypothesis. It's basically doing induction. Sometimes you need to make a very strong induction hypothesis to get the conclusion you want, but the conclusion itself is actually much, much weaker than the bootstrap hypothesis you make. And this is the situation here. So this is some pictures. You have the full solution. We cut into pieces using the midpoints of expected locations, but these filaments are always created and they will cross the border. And then once they cross the border, they start to interact again with the original part where this filament came from. Okay, so I'll just briefly explain how the proof actually goes. So this is the list of bootstrap assumptions we want to close. And there is global conservation laws, L2 norm squared, and the impulses. So while each of these quantities are changing in time, the square sum is conserved. And in the case of impulse, it's a linear quantity, the sum is conserved. And energy is more delicate because energy is not sum of the individual energies. There is also interaction energy term. That's why in the case of energy, we need to put bootstrap assumptions for both of them. So here's a typo, here's kappa 1 and mu 1. But in the case of kappa 1 and mu 1, we just need to propagate for one of them because of this global conservation. And the main enemies are filamentation and the lift-off effect. And let me describe the lift-off effect. When we start with two identical lambda dipoles. So if we start with identical lambda dipoles, you see that it is not stable. They collide and become a large single vortex. And this is caused by this lift-off effect. And you see, if you remember this point vortex picture, this is exactly the effect which gives this leapfrogging phenomena. So let me just show you it once again. So what happens is that the dipole in the back lifts up the dipole in the front. And once it's lifted, it becomes slower. That's why it's being caught up by the follower. And I want to emphasize that we are starting with two identical ones. So if there are no interactions, they should just shift identically. But because of this lift-off effect, the follower definitely becomes faster, no matter how far they were initially. And the effect of filamentation decreases the quantities of the first guy, and it can be seen directly from this time derivative computation. And it's easy to control large filamentation, potentially large filamentation from omega 1 to omega 2, if we have a priori lower bound on the energy. To have this lower bound of energy, you cannot lose too much mass from here to there. Okay? This is reasonable. But the key challenge is to control the lift-off effect, because the follower increases the impulse of omega 1, but we need upper bound on the impulse of omega 1 to apply the kinematic theorem. And this second term, this big integral, is exactly the amount of lift caused by the follower. And the difficulties treating this lift-off is purely technical. It has a singularity near the borderline. And there are always particles crossing the singularity from filamentation. So the way we treat this is to apply primarily a Lagrangian argument. So in this lift-off effect, we distinguish two types of particles. The first type is what we call separated particles. It means particles which are separated from the first guy for globally in time. And their effect is negligible by the same reason in the point vortex case. Once you have separation of support in the physical space, then we just use the decay of kernel. There are no issues. All the change comes from the lost particles. There are particles which were initially in omega 1, but those who migrate to omega 2 by filamentation. And they gives potentially large lift-off because of singularity in this kernel. And this we bound by Lagrangian argument, meaning we track the trajectory of each lost particle and get an upper bound on the total lift each particle can give. And here the point is that we know at this stage the total mass of lost particles is small from having small filamentation. However, having small filamentation was based on having a lower bound on the energy. And there is nothing kinematic preventing large energy escape. This is existence of an energy favorable regime or unfavorable depending on your viewpoint. And to close this, we make a new crucial observation, which is to actually compute the time derivative of the individual energy and relate the energy flux, the amount of escaping energy through the borderline. We can connect this directly with the flux of impulse. So in the end, everything is connected. We know that the flux of impulse cannot be too large, assuming we have energy trapping, but we have energy trapping because if we actually compute the time derivative of energy, the amount of energy which can escape is bounded in terms of the amount of impulse which escapes. So it's like a circular argument which closes due to the smallness, extra smallness in the energy computation. So this is basically the overview of the proof. I just want to briefly mention that lambda dipole is just a special case. When we use L2 in the admissible class, we can use any LP, P strictly larger than 1, and repeat the same thing. So in this generalized admissible class, you can find the maximizer. Maximizer is stable, and we can also consider multi-soliton stability for maximizers in this generalized class. And almost final slide. And of course, we are working under the assumption of the sign condition and the odd symmetry. And removing each of these conditions, has its own challenges. We hope to address these issues in the near future. And finally, for fun, I want to show you some simulations which seem very difficult to rigorously prove, but very spectacular in my opinion. So this is the simulation when you collide two lambda dipoles moving in opposite directions, but they are identical to each other. Then they collide, and it seems that they become again two lambda dipoles. But I really have absolutely no idea why this has to be true. And you can even consider the case of non-parallel collision. This is even harder. But you see some clear pattern. And the point is that almost all problems in the interaction of dipoles are completely open. And I really hope that in the near future, more people will join this interesting topic. That's it. And thank you very much for